So this is the voiceover of my Lab 1 report, and this lab was on constant velocity. So the purpose of this lab was to observe, model, and analyze the one-dimensional motion of an object moving at constant velocity. The models we used were the constant velocity model, where if the net force equals 0, then the change in momentum also equals 0. This means that velocity is constant since there was no change in momentum. The computational model we used was a numerical method to update the object's position. This formula was position new equals position old plus velocity times the change in time. We looped this calculation over and over to predict the object's entire path. The fundamental physics principles used was the momentum principle, which is Newton's second law, that a change in momentum equals net force times the change in time. The change in an object's momentum is equal to the net force acting on it times the time interval. If the velocity is constant, the momentum is constant. Therefore, the change in momentum must be 0. In this presentation, I will show that an object with 0 net force exhibits constant velocity motion, and our computational model based on the momentum principle closely predicts the observed trajectory. Some key assumptions were that net force is 0. We assumed that all the forces acting on our moving box balanced out to 0. And then the motion is 1D, so the object doesn't move towards or away from the camera, and that there is constant velocity was assumed since net force was 0.
Depending on
And the system is the moving object that looks like a box. The surrounding was the track, which exerted a normal force, possibly had some friction, but that was not included in our results because it was a very small value, if there was any. And then Earth exerts a gravitational force, air exerts gravitational force, and we assumed that all of these forces can added together to create a net force of 0. As you can see, I recorded a video of a box-like moving object moving across a smooth track. And the initial conditions was that at time 0, the x position was 0.04 meters. And then, since my object does not move vertically, only x value positions were tracked, and y was assumed to always be 0. So this was the experiment after we set it up. We calibrated a distance using a ruler measurement of our box so that the tracker application could convert pixel distances into real-world meters, ensuring our position data was accurate. Next, we began tracking the object. We placed a data point at the front of the box for every single frame of the video. This generated the trajectory you see here as a pink line on the screen. The time interval between these data points, dictated by the video's frame rate, was approximately 0.034 seconds. And then our total time interval from start to finish of the motion was 0 seconds to 0.53 seconds. And then we took all of this data and plotted it in Excel and created a graph which revealed a strong linear relationship between position and time, which is the defining characteristic of motion with constant velocity. Next, we had to test this with a computational model. Using GlowScript, we built a model based on the momentum principle. We used the same initial conditions, the starting position of 0.04 meters at 0 seconds, and measured velocity from our tracker data. Using the graph, I created a line of best fit and used the slope value for that as the velocity, which was 1.08695 meters per second. And then using this data and the same 0.34 times stamp, we generated an ideal position time graph for an object with 0 net force to compare directly with our real-world applications. And on the screen, I have the important code screenshotted, and just because it's a little small, the position update was ball.pause equals ball.pause plus ball dot veloc times delta t, and that's applying the momentum principle, which is Newton's second law. And then the timestamp update was t equals t plus delta t, and then you can see some of my initial conditions there. So here was the computational model next to the observed motion graph. And as you can see, the linear prediction from our model, which assumes constant velocity, matches the observed data points very closely, and this confirms that the net force on the object was approximately 0. Some similarities and differences between the data and model predictions. The key similarity is the linear trend, which confirms the physics principle that 0 net force results in constant velocity motion. The differences are not flaws in the principle, but are due to the idealizations of the model and unavoidable human experimental errors. The model perfectly describes the ideal case where our data represents the real world, where tiny forces and measurement errors exist. So some of those sources of error were a parallax error. The camera might have not been perfectly perpendicular to the plane of motion, and then human tracking error. Small pixel uncertainties when clicking on the object and tracker. Also, the timestamps might not have been exactly the same each time. And then there was model simplification when we assumed perfect constant velocity and exactly 0 net force because we ignored tiny effects like air resistance or maybe some friction. What if we flipped the axes? Flipping the positive x and negative x axes would change the sign of the position and the velocity values from tracker. The magnitude of the velocity and the shape of the position time graph, a straight line, would remain identical. Our model would still fit perfectly. We would just need to use a negative velocity initial. What does a net force of 0 mean? Our model requires that the net force equals 0 to fit the data. This doesn't mean that there were no forces acting on the object. It means that all the forces added to 0. There are at least 2 forces, gravity and normal force, that cancel vertically. And then for the horizontal motion, it could be an applied force balancing friction, or friction is negligible, no significant horizontal forces were present. We can't know the exact number or identity of the forces from this experiment, only that their vector sum is 0. We successfully captured the motion of an object using tracker to extract data and built a computational model based on the momentum principle. Our final result was that the agreement between the model and the observation confirmed that an object with 0 net force moves with constant velocity. Thank you for listening.